is exactly the gap this work addresses. The contribution here is a multimodal fusion system combining YOLO v5, CLIP, OCR, and DistilBert, achieving a 93.3 percentage of classification accuracy on live dark web data end to end. Let's see related work in this space now. Papers like Darkbird, written by Jin and others, is a dark web specific language model which is strong but on text only and not end to end. Similarly, he and others have worked on the space using text only but with no visual components. Axtas and others also took the visual route using Clip, hit 93.6% accuracy, but could not create a live end to end pipeline. Rawat and others, they tried to use a multimodal fusion method, wherein was they reported only 84.25% of accuracy on simulated data, but not on end to end. This system, which we are proposing, works on this both multimodal and fully end to end, and operates directly on live onion URLs. So with a competitive 93.3% accuracy. The key takeaway from this table is simply that there is no prior work that process all four columns simultaneously, and this one will. So let me move on to dataset and data acquisition. A model is only as good as its data. Since there is no suitable dark web multimodal dataset that was publicly available, we created our own. The dataset which we created was almost 1,500 annotated screenshots of live onion sites covering multiple illegal categories like weapons, drugs, malwares, and fake IDs. For data acquisition, we use Playwright library, controlling a headless Chromium browser with all the traffic routed through a Tor proxy. The scraper handles the JavaScript heavy dynamic pages, captures the full page screenshots, including lazy loaded content. Coming to annotation, we used a dual strategy. For visual annotation, the bounding boxes were drawn around the embedded images in each screenshot and saved in YOLO text format. For textual annotation, each screenshot was then manually assigned a category label for training DistilBert. A lightweight custom HTML and JavaScript annotation tool was built for this purpose. Now I'll be moving on to system architecture. The input is a single .onion URL. The first step is to extract the screenshot. It moves to the screenshot extractor. The Playwright library routes the request through Tor, renders the page, and captures the full screenshot. From there on, two streams occur parallelly. First is the visual stream and then the textual stream. In the visual stream, YOLO v5 detects and localizes embedded images on the page, and then Clip semantically interprets each of the image using a zero-shot classification. In the textual stream, Tesseract OCR extracts all the raw text from the screenshot, and DistilBird classifies that text into one of the illegal content categories. Both the streams are then fed into a hybrid fusion model, which produces the final classification. The whole of the software stack runs on Fast API for the backend, PyTorch and Hugging Face for the ML, and MongoDB for storage. Now let me zoom into each of the four components. YOLO V5 is our image detector. We custom trained it on 1,500 images, achieving an mean average precision of 72.7%. It locates the embedded images within each screenshot and then returns the bounding box coordinates. Clip is an OpenAI's model that the which then receives the cropped images. Because it supports zero-shot classification, no category specific training is required. So thus it returns the highest scoring text prompt for each image, such as a photo of a weapon. On the textual side, we see Tesseract's LSTM engine processes the full screenshot, performing the layout analysis and character recognition to return a raw text string. That text is then sent into Distilbert, fine-tuned on an OCR extracted text from the annotated screenshots. It is trained over 3 to 5 epochs, and we achieved an standalone accuracy of 87.7%. Each component is independently auditable, which which then ties to the fusion design, which I'll be explaining next. So, fusion model, this is the most important part of the system. The fusion formula, as you can see, combines textual, visual, and then gives a collaboration score. So what this means is we give 60% of the weightage to our Distilbert confidence score, wherein we prioritize text because it has a higher standalone accuracy. And then we give 30% of the weight for the images, which for the normalized count of clip captions that match the keywords for the for each category C. Then we give a corroboration bonus that is 10%, which is applied only when both the streams independently agree on the same category, rewarding cross-model consensus. Now, a natural question here would be why rule-based fusion method is applied here instead of a learned attention mechanism. There are two reasons. First is forensic interpretability. Law enforcement generally needs to audit exactly why a content was flagged. Thus, a black box neural fusion layer does not allow this. This formula does. That is why. And second, data constraints. With 1,500 images, training a reliable, learnable, multimodal fusion layer would be statistically unsound. So the rule-based principle approach is both principled and practical at this scale. Now let me go to evaluations and results. The hybrid system which we built achieved an accuracy of 93.3% on live onion URLs, correctly classifying almost 28 out of 30 URLs against the baselines, that is 20.6 percentage points over the clip baseline, which is at 72.7 percentage, and 5.6% percentage base points above the text only Distilbert baseline at 87.7 percentage. The large gap over the visual baseline shows that the image analysis alone is clearly insufficient for dark web content. The improvement over the text baseline confirms that visual evidence, even at a lower weight, meaningfully contributes to the final decision. Now, it is important to note that the two misclassified cases are worth here. In the first case, the page had minimal text and poor quality images, where both the streams returned weak signals. In the second, the evasive language had bypassed Distilbert, while the images appeared benign, so neither of the stream could flag it independently. And it is also worth noting that the live evaluation set is intentionally kept small at n is equals to 30, where due to ethical constraints and we could not do it, find so many URLs in the dark web too. Next,
Yeah.
I'll be
So
moving
after
on.
sir, so we'll be yeah. So you can
Hello.
conclude. Yeah, you can conclude. That's fine.
Yeah, yeah. To conclude, this work proposed a multimodal framework using YOLO, CLIP, OCR, and Distilbert to automate dark web content classification. A custom annotated dataset was created of 1,500 dark web screenshots, and a fully operational Tor end-to-end pipeline was built. The weighted fusion model formula ensures decisions are interpretable and forensically auditable. In terms of limitations, the live evaluation set is small due to ethical constraints, and the system is currently English only. The fusion weights are static. We know that. and captcha and authentication barriers are not yet addressed. Future directions would include multilingual support, learnable fusion through cross-modal attention, adversarial robustness, and ethics first deployment protocols for law enforcement use. Thank you. And that brings me to the end of this presentation. Thank you all for your time. I would like to thank ISDFS organizing committee for this opportunity and Dr. Jenny Jijo for her guidance throughout this work.
Hey, thank you so much, Akash. So any Q&As for Akash? So if not, so we'll move on to our next paper. Thank you so much, Akash. Thanks for your time. And our next paper is like paper ID 251, titled SEAL, Sequential Evolving Alert Learning for Smart Cybersecurity. This paper is presented by Riona V and R. Hamalata. Please join me in welcoming them to the floor.
Thank you, sir, for this opportunity. Can I share my screen, sir?
Yeah, go ahead and share the screen.
1 second, sir. Good day, everyone. My name is Rihanna, and I'm here to present my project, Sequentially Evolving Alert Learning, SEAL in short. So, what's SEAL? SEAL stands for Sequentially Evolving Alert Learning, as we all saw. It's an alert prioritizing model which is used in security operation centers in most of the companies. So, what the main reason why I've did this project is to address a major issue, like the amount of alerts we get in a company every day. For a major company or a minor company, the number of alerts we get for a second is varies from 10,000 to 20,000 alerts. And mostly people use models, but human are also involved, and going through all those alerts is a major problem. So I've developed a system using machine learning, random forest and XGBoost to achieve an accurate classification, to classify the alerts into three prioritize, high, medium, and low, and to help the security operations centers to keep a smooth company and not have any alerts. So there are many existing systems that has machine learning to prioritize the alerts, but the main reason why seal differs from it is I've made it like it's like an fully AI system. Like every other system, existing system has a function called as hat, which stands for human and AI team, which means whatever, even anything the system does, it needs a human verification. So without a human validating the work, the AI cannot work or the system cannot work. But seal is not like that. You only you only need seal during the initial model training, and after that, if you're retraining it, only then you need an human intervention. Other than that, seal can perfectly work on its own. And let's go to the in the abstract, it's the same. In SOC companies, in day-to-day life, we have major cyber threats, cyber security threats for every company. So with the demand, we have a demand for even high intelligent systems to adapt to this intelligent world. So that's when seal comes in, which is used to detect and classify the threats, and it's also used in real time. So when you connect seal to the live server of the company, it'll gather the alerts in live, like with a time duration of 3 seconds or 4 seconds, based on the time duration the person keeps. With the time duration, it again reshuffles the alerts and arranges them in the prioritize high, medium, and low. And It uses the two models, XGBoost and Random Forest, and the total accuracy seal has obtained is up to 97%. The data set which I have used, I have gathered it from Kaggle. So yeah, the proposed system is also the same. Like there are three the reason the proposed system is different from the existing system is it has adaptive threat detection. We used machine learning to detect the suspicious patterns. Like how it detects the suspicious pattern is like it checks the protocols TCP or UDP, the servers, the number of packets, the byte transferred, the duration, or the traffic behavior, and like combining the patterns. Like if it's having like high packages plus traffic behavior, it'll prioritize it as high, or else it'll keep it in the other priority levels. And sequentially alert learning part, it can continuously learn and evolve based on the new observed patterns or threats. That's where the XGBoost comes in. And real time alerts, like it's not just like it will save the alerts and then it will show the alerts. When it's connected to the live server, it will automatically and in live it will prioritize the alerts. And when we have like high alerts, it will notify the user that we are having potential cyber attacks, which enables a fast response. And reduce in false accuracy, like we will have false accuracy in the beginning because that's when it's working, but going on it'll learn from its previous mistakes and it'll evolve and it will give us a perfect result going further. And the architecture model first, it collects the raw security logs and then it processes the modules. And the seal does not need every feature of an alert. It only needs few extracted features, like I said, TCP UDP protocols or IDS or the source or the high packages, the counts. And with that, we've trained the model, Random Forest and XGBoost. We've trained it, and then we've labeled the, like we have three labelings: low, which is 0, and medium, which is 1, and high, which is 2. Within these three labeling, it will store the data, and then it goes to predicting and prioritization, where it predicts the future data, and also with the help of the data it stores, and it will show the data in an like streamlit dashboard view: high, medium, and low. So as I said, first the First, the raw security logs. When it's connected to a live server, it gets the raw security logs from the server. Then it processes the modules, and it only extracts the features it needs. And with the help of the random forest and XGBoost model prediction, it labels the alerts and it predicts them and prioritizes them. And alert database, it shows it in the Streamlit view. So we have total of five modules. First is the data acquisition and processing modules. This is when the seal, like this is the foundation of seal. So it continuously collects incoming alert data from the source, such as firewalls or intrusion or the live servers, and then it cleans the data. It does not need all the process. It removes the duplicate files and missing values. It doesn't care if there's missing values. It will take care of it. It will then turn it into a numerical form. Then with the help of the models, it will analyze, and then it converts the raw network logs into a structure and AI ready input. Then it goes to the prediction part. Why SEAL is called as an intelligent alert classification model? The brain of SEAL is the XGBoost and random forest model. As we all know, random forest model is a tree classification model where it gives us multiple varieties of outcome, and and it compares all the outcomes, and which has the highest probability, it gives us that as the output. And why we use XGBoost? XGBoost is the reason I use XGBoost is for future enhancement. Like we will have like few false accuracy or new alerts. So to analyze those false accuracy and new alerts, it retrains the system so that it can also it can also prioritize the new alerts and reduce the false accuracy. So yeah, sequentially evolving self model and the visualization and the dashboard module. Like the dashboard consists of two parts. One, in the sidebar we'll have like number of alert counts you want to see, and the time interval in which the alerts must be like refreshed and it must be prioritized again, so that it will be easy for the SOC team members to see which alerts, and then they can refresh and they can take care of the new alerts. And also the alerts, like first number of alerts per category, like high in the top and then medium and then low, and then confusion matrix like and live graph, confusion matrix for the XGBoost and random forest, and live alert graph, like how much low alerts we've got, how much medium alerts we've got, and how much high alerts we've got, to show that we have the live alert graph. And the alert management and integration module, this module acts as like the communication layer of the seals. Once the alerts are classified, this module automatically notifies the administrator, like only for high alerts, because medium and low we can take care of them, but high alerts need to be prioritized immediately. So when we get high alert notification, the seal immediately triggers and notifies the user. So what this does, when the user is notified of high alert, they will immediately go through it, they'll take care of it before we have any breach or any damage done to the company or the website or such.
Hey,
And
so we are almost at top of the presentation. So can you please?
okay, sir.
Good.
I'll just go to the advantages. So, as we saw, the advantages were the self-learning part, where SEAL does not need to be like constantly like retrained, or we need a human. It can self-learn, and real-time detection triggers, like when we have like high alerts, it will respond immediately, and false positive, lower false positive, like it reduces, it will train and it will reduce the low alert sorry like low false alert positive. And this is how the Streamlit dashboard looks like. As you can see, we can see the number of alerts per update and the interval, and the number of alerts I needed it to display, and it will prioritize them. And for future enhancement, what I've thought in mind was, why not just show all the alerts? We can also group those alerts. For example, all the alerts don't come from different person. Few alerts may come from a same person or same company. So we can group those alerts, and which will be easy for the SOC team members to analyze and take care of them. And report writing. As per my research, the highest report a person can write in a week is like 3 to 5 reports. So but we get more than 10,000 alerts per second, so the count, it varies, it's like significantly greater and this is significantly less. So while using AI to generate these reports, it will gradually reduce the time and say it's very time efficient. And a conclusion, SEAL is like a fully automated AI based classification system for smart cybersecurity monitoring. And with the help of random forest and XGBoost, I've obtained a percentage of 97 percentage. And Like with this model, I feel I can like with the new data we can get from the company, we can retrain the model, and this will be a great impact in the society for the soft people. That's also.
Hey, thank you, Riona. So, any questions for Riona regarding her SEAL project? Okay. Let's move on to the next item. So, it was presented by me. So, let me share my screen real quick. So my name is Surya Veer Brahmajira. So I'll be presenting today the large-scale financial forecasting using the advanced AI-based large language models and time series analysis, and with the paper ID 255. Second. And I'll be quickly going over the abstract of this. Uh, so what we have doing is like we are proposing a hybrid financial forecasting framework using like a 200K historical and S&P 500 records to compare the ML and GA based deep learning models. And we also applies the systematic pre-processing, featuring engineering and handling the missing infinite values and missing the normalization and time order splitting. So we have used the XGBoost to capture the nonlinear patterns in the structured financial time series data, and also we employs an Albert-based transformer model to learn long-range temporal dependencies through attention mechanism. With the Albert, we achieve the superior performance and the outperforming XGBoost and LSTM models. And we also demonstrated the lightweight transformer architecture provided accurate and scalable forecasting, though with the higher computational cost. And let me quickly go over the introduction, and I don't wanted to talk about all the things, but I just wanted to explain the transformer based architecture and the LLM if effectively capturing the long range dependency using the attention mechanism. And I also wanted to point out the limitations of the existing methods, which includes the short term focuses and the high computational cost and the lack of the robust pre-processing pipelines. And also we proposes a scalable hybrid framework using the extensive future engineering and the lightweight Albert based transformer efficiency in the high accuracy forecasting. So here is my literature review, but I don't want to go over this one. So we'll go with the methodology what we have introduced. So we went with the S&P 500 stock data sets, which has a large historical time series data set used for the forecasting analysis, and also we have used the data pre-processing, which includes the future engineering, handling missing infinite values, and also the min max normalization, and also the data splitting, training and testing, chronological split to prevent the data leakage and ensure the fair evaluation, and also the model implementation which we have used, which is like a XGBoost and Albert. XGBoost for the non-linear patterns and the Albert for the long-term dependency learnings, and also the performance measures, which is like a RMSE, MEAE, and MAPE to evaluate the prediction accuracy. And as a result, like the comparative analysis to identify the best performing forecasting model. And coming to the result analysis and the discussion. So we have compared the table 2, which compares the performance between the XGBoost and the Albert models using the standard regression metrics. While the XGBoost achieves the competitive results, and also the Albert demonstrate the superior performance, which a higher R square value of 0.9930 and significantly lower RMSE and MEE values. Overall, the result confirmed the effectiveness of the Albert model for accuracy and also the reliable large scale financial forecasting. And if you watch for the figure 2, the training and the testing loss curves for the Albert model. So in this context, the MSE versus the epoch, the training history of the Albert model. So the training loss abruptly decreases in the first epochs, and then it decreases slowly, which proves the effective learning and the steady convergence. The testing loss is highly consistently small during the training process, which indicates the high ability to generalize as well as the significantly overlifting the model. And here the result still continues. We'll go with the figure number 3, which talks about the overtime with the XGBoost. And this XGBoost model residual, as the time passes through the test dataset, the residual is the table centered on 0, and this means like the predictions are made unbiased in general. However, the value of the residuals are larger in the later time indices. So this trend implies an increase in the error of the prediction of larger stock prices, and also indicates the inaccuracy of the model to explain the large changes in the prices. And well, coming to the figure number 4, so this is the scatter plot of the XGBoost model, and the actual forecasted pricing is shown in the figure number 4. So this is a high forecast accuracy throughout a wide price range, since the majority of the data points are around the ideal prediction line. Nevertheless, there is a minor deviation at higher price values, indicating a lack of accuracy in the extreme price movements captured. So these are the tables which we compare between the XGBoost, Albert, and RF and LSTM. So what we have find out is like the forecasting model using all these models. So indicating like a weaker performance, while XGBoost achieves like the model accuracy. So Albert records the lowest RMSE, which is like a 4.30, and also the MAE is like a 2.14, demonstrating the best predictive accuracy and more consistent behavior, confirming its superiority with the over the traditional ML and DL models. And I would like to conclude this with a feature scope, like a growth in large data sets and computational power has advanced the financial time series forecasting, and GAI based transformer models effectively capture like a non-linear and complex temporal market platforms patterns. And Albert achieves like the best performance, as we have taken out the S&P 500 Kaggle datasets, and that's where like we have done so much analysis on that, and also the with the lowest RMSE and MAE, which shows like the high accuracy and the robustness. XGBoost delivers the competitive results, but struggles with the substantial price variations, while the LSTM shows the significantly higher errors. And we have used the lightweight transformers combined with a stronger pre-processing and future engineering provided on the efficient forecasting solution. And we all there is also like a study limited to the S&P 500 data. Future work includes asset validation, and also the macroeconomics of news future and advanced hybrid models like TFT, GNN, and reinforcement learnings. So this is how we have done with the financial data, and here are all the references which we have used in our paper, and that's all. Any other questions? If not, I'll move on to the next paper ID, which is like a 259. So drone assisted remote wellness monitoring using RGB camera. So this study comes under from Igman Bora Tusculum and Ishan. The floor is yours. You can go ahead, both of you.
Can you hear me? Can you hear
Yep.
me?
Yeah, we can hear you. Go ahead. We are able
I
to see your
shared the
screen.
screen. Can you see this?
Yeah, we are able to see your screen.
You can see the screen?
Yeah, we are able to see your paper now.
Okay, great.
Yeah.
Hello, everyone. My name is Egemen Bora Tuncasan from Maltepe University. In this section, I would like to briefly introduce the motivation behind our work. In emergency scenarios such as rural areas, disaster zones, or severe weather conditions, response teams often cannot reach patients in time. In these situations, even a limited psychological snapshot can directly improve remote triage and decision-making. Unmanned aerial vessels can act as first responders by providing rapid visual access. However, Extracting psychological signals from RGB video in real-world conditions is inherently unstable due to motion artifacts, low sampling rates, and intermittent phase detection. This creates a critical risk. Systems may produce outputs that appear plausible but are actually incorrect. In safety-critical scenarios, this is not just an error, it is more dangerous than producing no output at all. Therefore, instead of maximizing continuous estimation, we take a fundamentally different approach. We explicitly decide when not to produce a measurement. If you go into detail of related work, most prior work in remote phototelomorphology and UAV-assisted monitoring focuses on improving estimation accuracy and robustness. However, these methods assume continuous estimation and continue producing outputs even when signal quality is insufficient. As a result, they generate predictions that appear confident but are not reliable. Our approaches depart from this assumption. We treat uncertainty as a first-class outcome, not a hidden limitation. Instead of forcing predictions, we introduce selective publishing, explicit refusal mechanism, and interpretable reason-coded outputs. This shifts the paradigm from continuous estimation to evidence-based decision-making. If we go into detail of system overview, the system is designed for drone-assisted remote triage. The UAV captures facial RGB video and streams it to an edge processor, where signals are analyzed and results are transmitted to a command center. The processing pipeline includes phase extraction, RPPG signal recovery, temporal stabilization, metric estimation, and a safety-driven quality gating mechanism. Each output is structured and contains a status indicator, the estimated metric, a signal quality score, and explicit refusal reason codes when acceptable. This ensures that every output is accompanied by its reliability context. If we go into detail of experimental setup, the system is evaluated using a real-time telemetry log of 3,448 samples. The effective frame rate is approximately 3.72 FPS, significantly lower than typical RPPG conditions. This is intentional rather than evaluation under ideal laboratory settings. We test the system under constraint and unstable conditions that reflect real-world deployment. The goal is not to maximize clinical accuracy, but to determine when the system should produce outputs and when it should abstain. If you go into methodology, the system begins with phase detection and extraction of skin-based regions of interest. If detection is unreliable, the system immediately refuses the processed. RGB signals are aggregated and processed using POS-inspired projection to isolate pulse-related components while reducing illumination sensitivity. Temporal stabilization improves signal consistency. We estimate non-clinical indicators such as heart rate and respiration rate. The core component is the signal quality score, SQS. which measure the strength of signals evidence based on signal clarity, spectral characteristic, and sampling stability. Importantly, SQS is not a confidence probability, it represents signal identifiability. A strict quality gate then applied, a metric is published only if sufficient signal evidence exists. Otherwise, the system explicitly refuses and returns a low-quality status with interpretable reason codes such as a low frame rate, missing signal, or sufficient data. This established a key principle. If the system cannot justify a measurement, it doesn't produce one. If we go into the detail of results and discussion, the system achieves high availability under strict quality constraints. Heart rate estimation reached approximately 97.7% availability, while respiration-related metrics remain above 90%. At the same time, the system actively refuses outputs when signal conditions are insufficient. For example, heart rate variability is completely disabled due to low sampling instability. The primary causes of refusal include low frame rate, missing respiration signals, and insufficient temporal windows. This behavior is not a limitation, it's a design decision. Instead of producing potentially misleading outputs, the system ensures that only evidence-supported measurements are published. As a result, the system delivers both reliable outputs and transparency failure information. We presented a drone-assisted remote monitoring system based on RGB video analysis. Unlike traditional approaches, the system prioritizes reliability over continuous estimation by integrating signal quality score and explicit refusal policy. The system produces measurements only when sufficient evidence exists. This introduces a fundamental shift from continuous prediction to selective evidence-based publishing. In safety-critical scenarios, this capability is essential. A system that knows when not to produce a result of inherently more trustworthy than a that always produce an output. Furthermore, this supported.
So we are almost top of the hour.
Okay, okay. Almost finished. Also, this work is supported by the Scientific Resources Projects Unit of Maltepe University. Thank you for your attention. I will be happy to take your questions.
Hey, any questions for the paper which was presented by Egmont? Yeah, thank you so much. Yep, let's move on to our next paper ID, which is like 284. Our fifth presentation today is YOLO's optimization for minute detection. This paper is a collaborative effort by Ashan, and we look forward for your presentation. You can go ahead.
Hello everyone, good afternoon. My name is Hassan. Can you see my slides?
Yeah, we can able to see your slides.
Thank you very much. So my name is Hassan. I'm from Sam Houston State University, Texas. Today I'm going to present one of our recent research, that is the YOLO 11S optimization for miniature detection. So the outline for the presentation start with the introduction, motivation, related research work. I'm going to explain a little bit on methodologies, and finally I'm going to explain on result and discussion. Okay. So first of all, like, what is a miniature? So as we all know, like in our fingerprints, we have like, some patterns. So those patterns are called miniatures. There is like almost like 30 to 40 miniatures in a fingerprint. And to examine the fingerprint as a forensics expert, it is very important to analyze those miniatures. So first of all, what is the problem? Because the miniatures are really tiny. So till now, all the forensics experts, they manually do this miniature extraction. They mark it by their pen, and they started analyzing with the similar kind of thing. So the problem is that the first thing is that only a few pixels is wide. The first one is ridge endings, and the second one is bifurcations. So those two miniature is little bit wide, but rather than everything else was very, very, very small. So the first motivation for this research was starting like, when like in our regular courses, we starting doing one forensic course. So from there, like, we learn about how to find out those miniatures. So those fingerprint analysis was very time consuming. To analyze one single I mean fingerprint, it took like almost like 30 to 40 minutes to analyze all the miniatures. So for that point of view, like, and moreover, like, those kind of stuff is very important for their integrity and miscarriage of justice. The second thing is that, this challenge is very lead to motivate of fingerprint analysis to the machine learning field. So that is also a one. And moreover, like, at this moment only FBI has their own system. I mean, it is not published like, what kind of model or what kind of mechanism they used, but they have their own system to cross the similarity of the fingerprints. Okay, so for the miniature detection, it is very limited research work is available till now. We in recent days, we found like 3 recent papers. The first one was like the study area is they do the miniature extraction and reach tracking, 3D printer recognition, high comparison precision. So the limitation for this research was very, very much like, the limited availability of large scale fingerprint data set, because this data set is very, very small. And they also detection of some fake fingerprints. The second one was like, they did some feature extraction, and they did some algorithm like some CNN and VGG19, so to match it up. So the main challenge is that, like, if it is the augmented image, so this kind of system will not work. And the third one, it is also the similar kind of thing. It is also very limited. Traditional enhancement method was used, and the computational complexity was discussed over there. Okay, so first question is that, like, why we consider the YOLO. So the first thing is that YOLO is very single forward pass, because it detects the bounding boxes and the underexplosive for the miniature. So the YOLO style detections are proven for small objects, but have not been sequentially adopted for the reach level forensics targets. So what we proposed? So first of all, we proposed a single pass miniature formulation. And the second thing is that we did some the architectural customization on YOLO 11S specifically. And third one, we implement the system for the forensic award training strategy. So that is very important, like, because this kind of thing need to be admissible in court, because, like, if anything happened, if the wrong person got caught because of those kind of miniature detection, it can be a big problem. So let's discuss about the data set. The miniature leap data set, it is a published data set. We found it, the bounding boxes was also prepared, the training and testing set was already being prepared. We didn't, because of the integrity, we didn't touch on anything. We used the same data set as it is. So this data set has a 520 fingerprint images with 7,253 bounding boxes. So it is already split into train and test, the 92% on training data and 7.69% on test data. So this data set has only 4 classes. So they only mention like, four among like 35 to 40 miniatures, they only consider like 4. The first one is ending. The second one is center. The third one is also the ending, that is a different kind of ending. And the last one is bifurcation. So the bifurcation, it is like in the instances are like 3,332. The centering has a 591 and the ending has a 3,402. So now come to the YOLO 11 family benchmarking. In the beginning, we try to implement all the subclasses of YOLO 11. Start with a YOLO 11 small, medium, nano, large, and XL. So the finding over here that the largest model do not generalize the better. So it means like, when we use the larger models like YOLO 11X, the accuracy was quite degraded to 66%. So that's why like, from that benchmark, we select like YOLO 11S, like YOLO 11S got the best and it is most fast considering the GFLOS. For the customization, we did like, 4 targeted customization. The first one we did is high resolution detection stage. So we did some customization, did some downsampling, and we added some layers in the high res detection stage to did some modification of there. The second one was like wider large layer channels to better encoding and rich microtexture is quite impressive. The third one was multi-scale reinforcement. That is also a customization on the layers. And the third one was a mid-level context pooling. That is the P3 level SSFT aggregations. So from those 4 customization, we saw that the high resolution P2 stage is quite key innovation. It means like, we got the maximum accuracy, that is 74%, and for the awarding the training configuration, we maintain the same configuration for all the models. That is the start with the optimizer. We use the Adam optimizer. The learning rate was like 0.002, and we use the warm-up 3 epochs, and the others are basically the same for the all YOLO models. So from the abbreviation, each customization was very impactful. If you can see from the left, the YOLO 11S, the baseline has the accuracy, we got like 72%. And when we did the P2 head wider, that modification on the layers, we got like 73.5%. That is the maximum accuracy we achieved. And this is also the same thing I just segregated in different ways so that everyone can understand like what is the accuracy and the recall changes. So you can, from here you can also saw that the third one is the P2 head is the maximum accuracy and recall. So
Hey, Ashan. So can you conclude? So we are almost at top of the
okay.
hour.
Yeah, so the center, I mean, it is not the best one. Like, I can't say that we got the 100% or maybe like 98% accuracy, but as a starting point of view, as a miniature detection, it was really impressive. Like, I can show you one picture over here really quick. I'm not gonna go to that because of the time limitations. So the left side one is our original images, and the predicted one, if you can see, both of the images was really like close. So like the model we customized, it is detecting the miniature very precisely. So for this research, the code is already available on the GitHubs, and that's all for today. If you guys have any question, you can ask me. Thank you very much.
Hey, thank you so much, Ashan. Like, any questions for Ashan, or else like we can move on to the next.
Surya, if you don't mind, like I want to leave, like I have another commitment. I had another meeting.
Yeah. No worries. Go ahead,
Thank you.
Ashan.
Thank you
No
very
worries.
much. Thank you very much, Surya. You have a good one.
Thank you. Thanks, everyone. So we'll go with the paper ID 297. Titled with Advanced Fire and Smoke Detection in Forensic Surveillance, a study with the context-aware augmentation and optimization. This work is presented by Paul and his colleagues. Please go ahead.
All right. Thank you so much, Surya, for the opportunity. I'll go ahead and share my screen right now.
Yep. We are able to see your screen now.
Okay. You can see?
Yeah, we can see you.
Okay, yes. Hello, my name is Paul, and I'm going to be presenting a study. And the goal of this study will be illustrated as time goes on in this presentation. But the title of our study was Advancing Fire and Smoke Detection in Forensic Surveillance. So this is kind of how the presentation outline is going to flow throughout the whole of this presentation. And we dive into our introduction. So everyone has had experience, or at least has a memory concerning fire outbreaks or fire conditions. And these uncontrolled fires pose a serious threat to both forensic investigations, and they often destroy critical evidence before responders can even arrive. But surveillance footage kind of shows early signs of fire combustion, but there's nothing yet that can be done up until it's noticeably visible for most cases. That's where this study comes into place. So this matters because manual video reviewing is often, why is this happening? Manual video reviews are often slow and inconsistent, and they can easily be misinterpreted by the time cases can be resolved or cases can be reviewed. And and there has to be a better way to kind of speed up response times and improve protection of both resources, and as well as also critical compartments that could lead or assist with an investigation. So the goal of this project is to develop a real-time fire and smoke detection pipeline using YOLO models. When signs of combustion appear, the system instantly triggers alerts, almost like a security alert that there's signs of combustion that's about to occur, or more like so a visual smoke detector. Here we dive into the related works of recent YOLO-based fire and smoke detectors. The first study illustrated the use of YOLO version 11 for CCTV, but it still misses faint smoke in cluttered scenes. If there's any obfuscation in the imaging, then those signs are going to be overlooked. Well, with the second study, it introduced a multi-scale convolutional attention to better detect small and distant targets, but with only a small increase in the inference time. Whereas with the third study, it added a non-local feature fusion to the YOLO version 11 for fire and smoke, thus improving the performance under under a specific occlusion while keeping real-time speed. Whereas with the last study, it used targeted hyperparameter tuning to improve precision, recall, and MAPs across the board without sacrificing any inference speed. Some of these techniques helped guide us through the process of coming up with an optimal solution. With the data sets, we utilize a RoboFlow, a Biosmoke version 1 data set from RoboFlow. The source link can be found over here with the link on the slide. And the training splits we went with a 70, 20, and 10 split, with the 70% mainly going towards training, then 20% was allocated towards validation, and the remaining 10% was put towards testing the system. So with the method, here we dive into the methodology behind this. This illustrates the structure of the default configuration file for both the N, S, and M scales, and they're going to later be split depending on what configuration is being chosen. As well as within this configuration, the default backbone C3K2 blocks, as well as also the spatial pyramid pooling kernel is also introduced. These are the genesis of what will be configured later on over the course of the experiment to help fine tune the configuration file to develop accurate or at least effectively performing versions of YOLO version 11. We first started with the CSP configuration and made acute changes in order to not disrupt the internal scaling splits. Some of the changes that were made were such as reducing the configuration repeats from 2 to 1 in order to increase time with fewer computational operations, as well as also changing the kernel size of FASTA pulling from a 5x5 to a 3x3. Then with the CSP configuration as well, the aim of making those slight changes was for feature early maps and for late stage feature refinement in order to help achieve a more accurate reading, and also account for background distortion or background occupation of the visual of what the model is seeing in real time. So cases like whereas fire is red or orange, and we don't want any misrepresentation because there's a red hat there or there's a fire truck present, which the system can easily misconstrue. So this modification was made in that context. Then with the spatial pyramid pulling, this just dives into a little bit of like the thought process behind changing that configuration to a 3x3 instead of the initial 5x5. And this was just to reduce the computational cost, as well as also the memory footprint within the pooling layer to allow for more accurate or allow for more resources to focus on the computational operations. Then the second configuration that was made was a convolution configuration. So every C3K2 block that was introduced in the earlier slides were changed to a standard convolution layer. Doing this reduced the memory access costs associated with splitting and concatenating the tensors of that are accompanied with the learning ability of a CSP block. And the replacement created a convolutional stream that is easier to deploy on legacy hardware, making for an increased compatibility. But sadly, the downside of executing this is at the cost of the ability to focus on spatial details. With the convolution configuration, this time the the spatial pooling kernel was left at the default 5 by 5 in order to maintain adequate context awareness and not sacrifice hallucinations or misrepresentations. Now, every single convolution layer is set to repeat at 1 in order to cross-check or re-verify what what has already been calculated or what has already been arranged in the earlier computation in the earlier computational processes. So when enforcing this, very shallow structure is kind of created, whereas it's a one layer per stage logic. This increases inference time surely, with accuracy being a factor too as well. But the thing that we're trying to account for, or trying to combat, was also making sure that that accuracy actually detects the fire and smoke as intended, and not various synergies that are obtained that have the same shape and color.
Hey, Paul, like we are top of the hour. Can you conclude?
Oh yes, not a problem. These were the results that were attained, and as we can see over here, the the convolution configurations perform the best of the most accurate. Um, and this is a visual bar chart of the results. The yellow default versions, they showed that they were inefficient, and the configurations for the node CSP were the most accurate, and the most efficient, depending on the use case. Um, this is a gigaflop or flop by accuracy chart, and it illustrates the computational accuracy that is yielded according to the amount of computing resources that are being utilized. And because of time, still going to speed through the rest. And this study showed us that replacing the CSP blocks with simple convolutions produce the most accurate models. But there's still a dependency of architectural choices depending on what the goal of the specific project or study is. Then there are fine-tuning methods that are available out there that can produce closer, more accurate and efficient results. As of this study, we came across accuracy and efficiency. They are almost parallel to one another to an extent. Only so much can be accounted for. And we concluded with model tuning supports faster alerts, but with better evidence preservation for chain of custody. In addition to also the convolution architecture being the most accurate model, as well as also excuse me, as well as also the specific variants of them being the variant S and M scale of convolution. Any questions and answers, and these are the references. Thank you. I want to say thank you to the ISDF committee for this opportunity, and we are very grateful. Thank you.
Thank you, Paul. And I'd like to go with the paper ID 377. Our presentation is the predictive model of urban air quality management using AI. So you can go ahead and start your presentation. Hey,
Can you
if you're
guys see
talking,
my screen?
yeah, we are able to see your screen, and you can proceed.
Okay. Hello everyone, I am Dulare. Today I will be presenting our research in predictive models for urban air quality management using AI. This work focuses on developing intelligent, scalable and explainable system to improve how we monitor and respond to air pollution in Sri Lanka. This research was conducted by 6 authors from Sri Lankan Institute of Information Technology, including myself. Our research Professor module the explainable AI framework designed to transform air quality management instead of relying on reactive monitoring. Our system enables proactive forecasting, spatial mapping, anomaly detection, and health-oriented alerting. The goal is to move from simple observing pollutant to actually predicting and preventing its impact. Air pollution is becoming a serious issue in Sri Lanka due to rapid urbanization and increase in vehicle emissions. However, the monitoring capacity is extremely limited. With only few automated stations and spare sensor network, this creates large gaps in spatial coverage, meaning many areas are effectively unmonitored. As a result, police response are often reactive rather than proactive. An AI-driven system can help bridge this gap by enabling early warnings, better planning decisions, and improved public health innovation. Moving on, these are three main challenges we identified. First, the air quality crisis itself. PM 2.5 level in Sri Lanka often exceeds WHO guidelines by 2 to 3 times, contributing to serious health issues like respiratory and cardiovascular diseases. Second, limited monitoring infrastructure. We only have a small number of monitoring stations, which make it difficult to understand pollution patterns across the country. Third, reactive policy response. Current system lack predictive capabilities, meaning actions and taken only after the pollution event occur. From our analysis, we identify several critical gaps in existing research. Most current approaches use isolated models focusing on either forecasting, spatial estimation, or anomaly detection, but not integrated them. Many studies also focus on predicting single pollutant using single models rather than multiple pollutants simultaneously. And another major issue is lack of explainability, which reduces the trust among policymakers. Additionally, there is no strong solution for census parity. No system provide health-oriented alerts, and anomaly detection method often fail to explain why events happen. Our research addressed all these gaps through an integrated and explainable frame. Our contribution introduced several key innovations. The Sri Lankan first hybrid machine learning model for multiple return forecasting. Second, explainable AI using techniques like SHAP, premature future importance for ensure transparency. Third is ensemble spatial estimation approach combining multiple methods to improve accuracy and handle sparse data. And finally, health-centric alert system that generate automated standardized warning tailored for well population. Our system consists of four main components. Hybrid forecasting. We combine Hashari matches the temperature fusion transform to generate accurate multi-pollutant forecasts that forecast for hourly. Second is spatial estimation. We use ensemble of models like Gaussian process, RVF, KNN, and IWD to estimate the pollutant in unmonitored area. Third is risk score alerts. Using Seedman and sequence-to-sequence models, we generate 24-hour AQI prediction and trigger health alerts. Lastly, anomaly detection and explainability. We detect unusual pollution events and explain their cause using advanced AI techniques. Move on. This is the system architecture. We use data from 2019 to 2024, which are collected by Central Environment Authority that have a meteorological data with all the pollution data need. At the end of the using the Flutter mobile application, we display the forecast and other alerts as well. For forecasting, we use hybrid approach. SARIMAX capture the linear patterns while the temporal fusion transformer model capture the complex nonlinear relationship. This TFT allows to provide attention-based explainability, allowing us to understand which features influence prediction. Our results show significant improvements, including over 80% reduction in RMSE for ozone prediction, outperforming baseline models by 15 to 80%. To address sensor sparsity, we developed an ensemble estimation model. This combined multiple techniques with additional geographical features such as elevation, land cover, population density, road proximity. This output is high resolution heat map of 1 square kilometer along the uncertainty estimate. Our models achieve strong performance with the R squared value about 0.9. For risk assessment, we use
Hey,
Seedman
hey,
to
Dular, we are almost like a top of the hour. Like, can you conclude a little?
okay, a segment differs to AQI signal to in the stable connection. This provide 24-hour forecast. And lastly, our anomaly detection model use the ensemble approach combining Cisco isolation plus one class SVM and use GRO model to predict future anomalies. And also SHAP to explain why this happens. Moving forward, we are planning to deploy with the system with the real data, scale computational resources for improved performance, and integrated additional data sources like satellite and IoT data, and also extend this frame this to other South Asian countries with this data scarcity. Uh, in conclusion, our research presented scalable and explainable proactive AI solution for air quality management. Thank you. I also like to thank you to the ISDF community for giving this opportunity.
Thank you so much, Dullar. And last but not least, so I would like to call upon the paper ID number 389. So to conclude our session, and the cross-language transfer learning for vulnerability detection and by directional asymptotic between the Java and Python. This is present by Adida, Mohammed, and Asim. And you can go ahead. Paper ID 389. So do we have anyone who will be representing this?
Yes, just a second. Adib Mahmoud is going to present.
Yeah, go ahead. So if you're sharing a screen, we're not able to see your. Yasmin?
Hello, can you hear me?
Yeah, we can hear you.
Oh, I'm so sorry for responding a little late. So right. Can you see my screen?
Yeah, we're able to see your screen now.
Okay. Hmm. Good afternoon, everyone. And I'm extremely sorry that I responded a little late. My name is Adiba Mahmoud from Tuskegee University, and I have my supervisor, Dr. Yasmin Rawashvi, present here with me online. And I'll be presenting our work on cross-language transfer learning for vulnerability detection, where we specifically study the directional asymmetry between Java and Python. So, modern software systems rarely rely on a single programming language. Does not rarely rely on a single programming language anymore. In practice, most real-world systems are polyglot. For example, Java for backend services, like almost in all the program, like different languages are used in like different services. Like for example, Java for backend services, and then Python for data processing, and something for the front end. Now, most vulnerability detection models today are trained on one language and evaluated on that same language. So this naturally raises a question like, do the vulnerability patterns these models learn actually generalize across languages? So based on that, our work focuses on two core questions. The first one is, do vulnerability detection models transfer across programming languages? And the second one is, if they do transfer, is that transfer symmetric across directions? In other words, if a model trained on Java works on Python, does the reverse hold also? To answer this, we make four main contributions in this paper. The first one is we constructed a multi-language vulnerability data set consisting of Java and Python samples, over 11,000 samples across 241 CWE types. The second one is we systematically evaluate bidirectional transfer under 5 controlled configurations. Third, we identify a strong directional asymmetry in performance. And finally, we provide analysis and practical deployment insights based on these findings. So our data set contains a total of 11,060 samples, of which about 6,000 is in Java and roughly 5,000 in Python. We collected this data from 6 different sources, including Juliet, OWASP, CVFixes, and GitHub. We also applied several preprocessing steps such as syntax validation, deduplication, and CWE mapping. And importantly, we use stratified splits to preserve both language and CWE distribution across training, validation, and test sets. So this is the main architecture of our model. Our model is an ensemble of 3 pre-trained transformers. One is CodeBird, another one is Graph CodeBird, and another one is CodeT5. So each model encodes the input code independently, and we fuse their representations using multi-head cross-attention. One key design choice here is that we freeze the base models, so only like 2.7% of the total parameters are actually trained here. Finally, the model performs 2 tasks. One is binary classification for vulnerability detection and multi-class classification for CWE prediction. So, to isolate cross-language transfer, we evaluated 5 configurations. One is Java to Java, then Python to Python, and this two serves as our baselines. Then Java to Python and Python to Java. These are our cross-language settings. And finally, a mixed training configuration. And we evaluate using the regular matrices like accuracy, precision, recall, and F1 scores. And we define transfer efficiency as the ratio of cross-language F1 to the corresponding baseline F1. Looking at within language performance first, the Java model achieves a very high F1 score of about 98.31%. In contrast, the Python model achieves around 76%. So this gap, we can call it like quite significant, and it likely reflects that Python is more flexible and less structured, making vulnerability patterns harder to learn. Now, here's our key result. So when we train on Java and test on Python, the model achieves an F1 score of 75.15%, which is almost 98% of the Python baseline. So Java trained models transfer very well to Python. Now, in the reverse direction, when we train on Python and test on Java, the performance collapses. The F1 score drops to just 1.76%, retaining only about 1.8% of the baseline. So what we observe here is a clear directional asymmetry. Transfer is not symmetric, and there is approximately a 43 times difference in effectiveness between the two directions. And Java trained models generalize quite well, but Python trained models essentially fail to transfer. If we go for par CWE analysis, and when we break this down by vulnerability type, we see that Java to Python transfer works particularly well for injection-related vulnerabilities, such as SQL injection, cross injection, command injection, then cross-site scripting. However, Python to Java transfer fails consistently across all CWE categories, with F1 scores typically below 5%. And why does this happen?
Hey, Adi, so we are almost top of the hour. Can you quickly conclude?
Yes, of course. So as a next step, we plan to extend this analysis to additional programming languages and explore how transfer behaves across different programming paradigms. To conclude, cross-language transfer in vulnerability detection does exist, but it is not symmetric. And then Java to Python transfer is highly effective, while Python to Java transfer largely fails. And mixed language training provides the most reliable and exact solution. So overall, our results show that cross-language generalization should not be assumed. It needs to be explicitly evaluated. Thank you so much for your time, and I'm extremely sorry for my broken voice, and I'd be happy to take any question if there is any question for me.
Yeah, any questions for Adiba? If not, so I would like to extend a sincere thanks. Thank you all for the presenters for sharing their hard work and insights with us today, from cybersecurity and the financial forecasting to environmental monitoring and the software vulnerability. So we have seen very good response from all the presenters and everything. And I will also want to thank your audience, both here and the VAX Academy Center 127, and those who joined us via the Zoom for your attention and the thoughtful questions and enriched our discussion. Thank you so much. Thanks once again for the fantastic session. This session is now officially adjourned. Enjoy the rest of your conference. Thank you.